Anytime we are factoring a polynomial, we want to ensure that we factor the polynomial completely. That is, every factor is taken down to its simplest form. Sometimes those forms are easy to recognize because they fall into our category of easy patterns. Difference of squares, difference of cubes, sum of cubes, perfect square trinomials. But sometimes you have to dig a little bit more and make sure that you're looking at every step of the way to make sure there aren't any leftover factors that need to be simplified. So in this video, we're going to look at a couple of different examples to ensure that we're seeing everything we need to see as it comes to factoring a polynomial. The first example that we're going to look at is x to the 8th minus 15x to the 4th minus 16. Now this has the feel of actually an AC method kind of question. So if you remember, what we're looking for when we factor a trinomial is we are looking for the relationship between this highest power and this middle power. And we want that to be a doubling relationship. That's where the square would come into play normally. Normally, we would have an example that would look like this, and we would walk our way through the AC method in order to factor that polynomial. But because this power, the 8, is twice the power that's in the middle, we can still use the same technique. So if I AC, I multiply negative 16 times the 1 that is the leading coefficient, and I get negative 16. And then my B is negative 15. So I'm looking for a product of negative 16 and a sum of negative 15, which means my factorization is going to be negative 16 and x to the 4th plus 1. That's my two numbers that multiply together to make negative 16 and add together to make negative 15. I can tell you with some assurance that this is done. I know that the factorization, there's nothing else that I can do to x to the 4th plus 1. It is two squares together, but it is the sum of two squares, not the difference, so we must leave that binomial alone. But looking over here, we can see that this certainly does fall into the category of difference of squares. So we take it to the next line, and we say that the difference of squares for x to the 4th minus 16 is x squared minus 4 and x squared plus 4, and then we have our leftover x to the 4th plus 1. Again, we check each one of these terms. We already decided that this one was done. This is the sum of two squares, so this one is done, and we hit another difference of squares. So here, we're going to go one more time, and we're going to work just on this polynomial right here. Difference of squares on this one, x plus 2, x minus 2, and we have our two leftover polynomials from the earlier steps. When you get to the end, if you want to ensure that you kept everything along the way, one interesting little trick that you can use is multiplying together all of these x's and ensuring that you got everyone. So x times x squared times x to the 4th would make x to the 8th, and that's exactly our lead coefficient, or our lead degree for the original polynomial, just making sure we got everybody in that respect. But carrying out this multiplication would walk us back through all of these individual steps. Multiplying these two would give us this one, and multiplying those two would give us that one, and then of course multiplying those two would give us the original polynomial. Working down, checking each step along the way, making sure you've covered everything. Let's try another one. In this example, we're going to start with 4 terms. And immediately upon seeing 4 terms in a polynomial that you are trying to factor, the advice is always going to be to look for factoring by grouping. That's not to say that there won't be situations where you'll be able to simplify, maybe combine 2 terms together. But more often than not, if they are 4 distinct terms, grouping is usually the first route that you have to take. Looking at these first 2 terms as a group, we can take an x cubed out of those 2, leaving us with an x squared minus 1. Looking at these 2 as a group, we can take a 27, leaving again the x squared minus 1, which was the ideal circumstance. We needed this parentheses to match that parentheses. We have our common binomial of x squared minus 1, and we have all of the leftover parts, the non-common parts, x cubed plus 27. we reach an interesting step. Here I see a difference of squares, and here I see a sum of cubes. Two extra factorings to do as we move to the next line. For the difference of squares, we'll split that first one as x minus 1, x plus 1. And for the sum of cubes, we'll split it x plus 3, x squared minus 3x plus 9, using our pattern that we established earlier in the lesson. We make sure this first sign matches. We make sure that sign is opposite. Nothing to factor here, nothing to factor there, nothing to factor there. This type of polynomial is a prime candidate for looking for the AC method. So if you wanted to try it, you would say AC is 9. That's 9 times the 1 that's in front of there. And looking for a sum of -3, so a product of 9 and a sum of -3. Well, if your product is 9, your only choices are 9 and 1, and then or 3 and 3. You need them to be the same sign because the 9 is positive. So they both need to be negative because the 3 is negative. So you would either have -1 and -9 whose sum is -10, or -3 and -3 whose sum is -6. That means that this is the most factored that this can possibly be. So all of these steps, trying the AC method on this last one, because it certainly looks like a candidate, all of those steps, we did everything that we could along the way, even though our initial work right here created a difference of squares and a sum of cubes. We took that step also, but couldn't go any farther thanks to the AC method failing on this final polynomial.